So I'll be talking about electroweak symmetric walls, and this is based on series of papers that I worked on with my advisor Yang Bai and my collaborators Joshua Berger and Nicholas Orlovsky. So let me first tell you what I mean by electroweak symmetric walls. So here I'm talking about any solitonic state with some which has some radius, so it is a finite size, so macroscopic size object, which has some interesting property that inside the solitonic state you have electroweak symmetry restored, or the Higgs vacuum expectation value equal to 0, or more generally either 0 or up to V or even larger. So the vacuum inside the soliton is different from outside, and outside, as we know, the vacuum expectation value of the Higgs is just the 246 GeV in the unit that I'm working in. And phenomenologically, the most important thing for us will turn out to be the mass of the object, the radius of the object, and sort of what is the expectation value inside the ball. But we still want to understand that from the microphysics. And our goal here is to basically understand how to form it, and also how to get a larger size object, because it turns out this is a macroscopic state, and usually when we have a macroscopic dark matter, we really want to understand how to get big objects and how to study them or do their phenomenology. So here is a stuff that I'll be talking about. This is also sort of a brief summary of what I'll be doing in this talk. So first question, so it's basically a series of questions that I'll be asking regarding this object, how to get it from microscopic physics. And the simple answer here is that you get some topological or non-topological soliton in the dark sector, and you add Higgs portal interaction to the standard model Higgs, and you can get this kind of object, and I'll explain how to do that. After that, I'll talk about how to form this kind of object in the early universe, and can it be a really dark matter. And here I'll talk about two different mechanisms. One is the thermal phase transition, and another one is the preheating mechanism. After that, I'll talk about baryogenesis, which we call catalyzed baryogenesis. And the reason we are even thinking about doing baryogenesis is because it is kind of pretty natural to think, because once the ball has electroweak symmetry restored inside, the electroweak Sphaleron rate is kind of unsuppressed inside the ball, whereas outside in the plasma, it is suppressed. And so it can actually catalyze baryogenesis, and I will explain what that is. And at the end, I will talk about the direct detection. And this is the most interesting part, because it turns out, unlike the usual particle-like dark matter, where you have sort of single hit in your detector, this kind of object actually can give you multiple hits in your detector. So this is called multi-hit signatures. And it turns out that the energy released could be much larger, that you can actually search for these objects in the neutrino detectors. Okay, let me start with the first part, how to get it from microscopic physics. So we learned in the past few days about monopoles. So here I'll be considering sort of simple dark monopole, where you have SU2 symmetry spontaneously broken to U1, and with some triplet scalar field acquiring vacuum expectation value. And here we are mainly focused, unlike Hofstad's case here, we are actually focused on the sort of what is happening inside the monopole, what is the structure of the monopole. And here I'm drawing the sort of the plot of the field profiles. So at the same, so R is the radial direction of the monopole. So we have a spherically symmetric monopole. R here denotes the sort of the radial direction. At the center of the monopole, we have the SU2 symmetry restored, that is this phi of R actually has vacuum expectation value 0. Outside the monopole, we have the SU2 broken, and the phi actually acquires some vacuum expectation value, which we denote by F here. And the radius of the monopole is just the inverse of the WK boson mass. So as shown here. Now let's see what will happen if we add Higgs portal interaction. So here I have a potential. So we have sort of the dark couplings in the dark scalar sector. We have the Higgs coupling, and then there is an interaction. So notice the sign here. So I have put plus mu h square sign here. And that is to say that if lambda phi h is 0 and if mu h square is actually positive, what this means is that the electroweak symmetry is always restored. So to get the electroweak symmetry breaking that we observe, we have to have some kind of lambda phi h positive and the phi field to acquire vacuum expectation value. Now it is pretty clear that we will get some sort of field profile for the Higgs because of this coupling. And now the idea is for the case where you have this mu phi square positive, mu h square positive, and lambda phi is greater than 0, inside the monopole where the SU2 symmetry is restored or phi has vacuum expectation value 0, the Higgs also is restored. The vacuum expectation value of the Higgs is also 0. But outside of the monopole where phi acquires vacuum expectation value, you have the electroweak symmetry broken, and you have the usual vacuum expectation value for the Higgs. And this is we call the electroweak symmetric case. Now there are a couple of other cases also. For instance, you can allow for small mu h square, which is negative. In that case, what will happen is that instead of complete restoration, you can have partial restoration of the Higgs wave, so that it is not even 0 or complete V, but rather somewhere in between. And or you can also have some interesting case where the Higgs vacuum expectation value inside is actually larger if you allow for some other coupling signs here. But in this talk, I'll be mainly focusing on this particular case, which is electroweak symmetric case. Okay, so I showed you how to think of getting the this electroweak symmetric objects by using this kind of interaction. Now let me move on to the early universe.
What are the units of the y-axis?
Good. Sorry. Yeah. So y-axis denotes a sort of the field value normalized to its vacuum expectation value. So phi is normalized to its vacuum expectation value. So one just means for the phi, it is F, its symmetry breaking scale, but for Higgs, it means its vacuum expectation value, which is V. So they are normalized differently for a different field. Thank you. Okay, so how to get it from early universe? So the main idea is we want to form the dark monopole, and we know how to form it using the thermal phase transition. So this is sort of the Kibble-Zurich mechanism. The idea is that when the thermal phase transition happens, you have this patches in the universe which are separated by some correlation link, have different direction of the symmetry breaking, which is phi. And then at the center, you basically form a monopole-like structure just from the directions are in the random in a way. And the initial formation, actually, the initial yield of at the formation depends on the order of the phase transition, whether it is first order or second order phase transition, which depends on sort of the temperature of the phase transition and everything. But this is not the whole story, because it turns out there will be annihilations. And the reason we care about annihilations here and not in some cases like gut monopoles is because here we are trying to form monopoles which are larger in size, and where the sort of the magnetic field strength is actually larger. So you will have some kind of annihilation. So the idea of annihilation, it depends on basically two scales. One is the sort of the free streaming scale, and one is the capture scale. Free streaming scale just means that how far the monopole will move before changing sort of the direction, while the capture scale just means that the distance between monopole and anti-monopole at which they will capture each other and just kind of annihilate. And sort of the annihilation actually freezes out when the W gauge boson in the dark sector actually go non-relativistic, and that gives you sort of what is the omega m s square, or what is the abundance that you get after the annihilation. This was first worked out by Prescale, and it turns out this depends on what is the value of the W gauge boson mass in the dark sector. And as I mentioned earlier, the size of the monopole is just the inverse of the W gauge boson mass. So for the dark monopole to be, the monopole to be a dark matter, the dark monopole to be a dark matter, you need really smaller size. And this is, of course, not what we want. This is pretty small size. We want big size monopoles. So you have to think some other ways of formation. And here comes the preheating mechanism. The idea of preheating mechanism is just like phase transition, but here you have control because it kind of depends on in the thermal phase transition, you form monopole at some symmetry breaking scale, then they annihilate. But here what happens is that since this is the non-thermal phase transition, you can form the monopoles and kind of freeze out the abundance itself. This was actually, I should mention, this is sort of not a new idea to produce topological defects using preheating mechanism. This was first developed in 90s by Linde and other people to form cosmic strings in global or gauge strings. So here we are applying it to form monopoles. The idea is that before the inflation happens, there is already a symmetry breaking. And so everywhere in the universe, you are sitting at this wave of the phi1. So in the phi1 direction, everywhere in the universe. Now there is a coupling between inflaton and the phi, which is given here. And when the inflation ends, the inflaton starts oscillating about its minima. And this leads to sort of the parametric resonance of the phi field. And this just means that there will be a fluctuation, not just in the radial direction, but also in the angular direction. That means in the phi1, phi2, and phi3 directions. And if the fluctuation in all of the direction are of the order of the symmetry breaking scale, that means when the preheating ends, you have the small patches where you can have the random direction of the symmetry breaking phi. And this leads to the monopole formation. And after the preheating ends, you can basically reheat the standard model to some temperature. It should be higher than Vivian, but anyways. And also you have to take care of the fact that the dark sector and the standard model sector is kind of decoupled, not thermalized, because you will also have some dark photon, and we don't want to mess up the Vivian. So you have to reheat dark sector to some smaller temperature than the standard model. So here is the parameter space that you get when you think about this kind of mechanism. So this is the parameter space in the this is the radius of the object, m is the mass of the object. The things that I want you to take away is basically that here you can have larger size monopoles, larger than, let's say, Electroweak size or even QCD size. And also you can have much massive monopoles larger than, let's say, Planck scale. So, so you basically opened up a parameter space in terms of this dark monopoles, but still there is sort of a limit to the sort of the maximum radius that you can go in this kind of a mechanism. Okay, so I showed you how to get the abundance, how it can be a sort of a dark matter, because you can produce it as a dark matter relic with correct abundance. Now let me move on to catalyzed baryogenesis. And why we call it catalyzed is because just to explain it to you what catalyst means in the chemistry, the idea is you have a catalyst, the particle comes in, get attached to this catalyst, the reaction happens, particles go on their own way, the catalyst want to catalyze another reaction. In a similar fashion, we have the baryogenesis happening because of these objects. So let's see how that happens. So let me first explain how to get the Sakharov conditions to do the baryogenesis. So as I explained earlier, the Sphaleron, you have the Sphaleron rate, the electric Sphaleron rate, which has this exponential dependence of the E Sphaleron divided by the temperature, and the E Sphaleron depends on the vacuum expectation value of the Higgs. Now, if the ball has vacuum expectation value 0 inside, that means that there is no exponential separation inside, but outside you can have a much larger separation. So you have this baryon number violation active inside rather than outside. Now the CP violation we are basically in a similar fashion as we do in the Electroweak baryogenesis case. You have to add some higher dimensional operator. Here we have coupling with some field, which is also the field in this Electroweak symmetric ball. When the field has a profile, so it depends on the radius. and when you try to calculate what is the mass, let's say here for the task ball, it has some phase theta of r, which is changing as a function of r, where r is just the radial direction of this ball. And so in the wall region, you have this radial dependence of the phase, which goes from 0 to something like f square by lambda square, where f is just the symmetry breaking scale of this phi. And this gives you the CP-violating interaction at the boundary of the ball, or at the wall region of the ball. And the local, the out of equilibrium is basically just similar to what happens in the electroweak baryogenesis case, that there is a movement of the wall with respect to the plasma. And so locally you'll get sort of the out of equilibrium condition. Now let's see how to generate baryon asymmetry. The idea is basically you write down sort of the diffusion equation for the CP asymmetry. The basic idea is that you have a ball moving in a plasma. So in the ball frame, the plasma is moving, let's say, in the left direction. Now, when the baryons and antibaryons interact with the wall, they have sort of a different transmission coefficient. So let's say on the right-hand boundary, you have more antibaryons going inside than baryons, while because of the sign here for the source term at the boundary, you have more antibaryons going outside than baryons. So, but there is also a diffusion because there is a net velocity of the plasma inside the ball. So what happens in the end is that you have more antibaryons than baryons at any time inside the ball. And now you have this kind of a CP asymmetry, which basically fits into your Sphaleron to give you sort of the baryon asymmetry, because this extra antibaryon is basically converted into leptons to give you the sort of the leptons. Now this is for one ball. Now you have to take into account like the number density and of the balls and sort of over longer period. And this gives you sort of the final baryon asymmetry that you can generate. And it turns out, and it's almost clear that you need a larger size ball and smaller mass balls to have a larger asymmetry. Okay, so let me now move to the last part, which is the direct detection. The idea here is that the only way the particles will interact, standard model particle will interact with the ball, is because there is a Higgs profile in your ball. So you have the Higgs profile, as I mentioned. And so the idea is that when the particle interacts, they will basically feel sort of a Higgs potential well, which has, and this is the spherical potential well because we have a spherical ball. The sort of the height of the well depends on change in the mass of the particles, and the radius is just the radius of the ball. Now, given this kind of setup, you can calculate what is the scattering cross section. It depends. It's basically sort of like a quantum mechanical scattering that we do, and you can calculate the elastic scattering cross section at large radius. This just becomes sort of like a geometric limit. So you can see what are the numbers here. These are the numbers which you can actually probe in your detector. So here is the sort of the limit plot. Here I'm showing 3 different experiments, so xenon, mica, and Juno. And of course, the dark regions are the exclusion limits. The sort of the vertical limit here just means that on the right hand side, the flux is too small to detect. And then there is a cutoff even here on the top. This means that there is something like when the cross section becomes large, there is a multi-hit scattering in your detector. Now let me explain what that means. So when we do sort of the WIMP dark matter scattering, you have a dark matter come in, scatter off a nucleon just once. So this is called the single hit scattering. But in multi-hit scattering, what happens is that the cross section is large enough that you can get sort of a track-like signature in your detector, where there is a sort of energy deposition which is separated by some distance. And it turns out this can be mimicked by a standard model process or even noise sometimes. So you have to be careful in designing your triggers and other things. There is another thing, which is since you are scattering out of a potential wave of a Higgs potential wave, there will be sort of a bound state formation also, where let's say some nucleon forms a bound state and release the binding energy. This could be, let's say, hundreds of MeV binding energy, and this energy you can basically detect at a neutrino detectors. And why we are going to neutrino detectors is almost clear, because these are really large volume detectors. And so we did that. We actually did a search at or more like a projection for the IceCube detector. The idea is that IceCube detector has this small sub detector which is more compact, so has sort of a less energy threshold, so something called as deep core detector. The idea is when the ball is passing through, it will release the energy, hundreds of MeV to GeV energy, which will then undergo electromagnetic shower, which will then produce this relativistic electrons, which will produce Cherenkov light, which you can detect in the sort of the small black detectors. And to build a detector, you actually, to build a trigger, you need the information for the time when the interaction is taking place, and also sort of the where it is taking place. And you have this kind of a track-like signature both in time and in space. And you can actually build the trigger. It is called slot trigger, and also the background is under control in this kind of a setup. And these are the constraints. So these are sort of the projected limits using 10-year runtime. Ex is the energy that you can release, the binding energy that you release in the interaction. Y-axis is just the cross section. The x-axis is the mass. The idea, as you can see here, you can't probe much beyond 1 gram, even with using this sort of big IceCube size detectors, because there is sort of a limitation from the volume of the detector, or the area, cross-sectional area of the detector. So let me tell you what we are thinking in terms of future direction. One thing, of course, is how to get new ways to get this electroweak symmetric balls. As I told you, there is sort of a limitation when you do this with monopoles. We want to get much larger sized object, even thinking about something like electroweak symmetric stars. I mean, why not? That is the reason why it is interesting, is because this could be formed in the early universe. This could also form binary stars in the early universe, which could leave pretty interesting signature, both in the gravitational waves, and when they merge, it is almost like you are colliding a bubble, which has pretty large energy. And so it will leave also interesting signature in the sort of the electromagnetic part also. Then other direction is just thinking about new ways of developing a trigger, or searches using the experimental data in the other neutrino detectors such as Dune or Hyper-K. And the idea here is that I only talked about electroweak symmetric case, but if you have partial electroweak restoration, in that case, the binding energy release will be order of MeVs, so much smaller. IceCube cannot detect those kinds of energy, so you need other neutrino detectors such as Dune or Hyper-K. And of course, as I mentioned, you can't do better than gram mass in the terrestrial detectors, so you need to also think of how to do astrophysical circuits. And let me leave you with the summary slide. So I basically asked a few questions regarding this electroweak symmetric ball: how to get it from microscopic physics, how to form it, how to do baryogenesis, and how to do direct detection. And here are the sort of the answers in pictorial form. So thank you for your attention.
Start. Questions? Yes.
So you mentioned the binding, like the nuclei baryon matter is very heavy both. So what happens if you just keep throwing baryons?
Yeah, at some point you will fill up all of the states in a way. So there is a sort of a limit to you can emit the because once you let's say you form a bound state, there will also be another interaction, because from the nucleon to other nearby states, and that will kind of stop at some point.
a very quick and dumb question. These electroweak balls, they're essentially a region of space where the vacuum is difficult, the field value is different than the vacuum. So presumably they have some pressure as well.
Good. Yeah.
Is it clear that they
They are
if I write
stable.
down equation of a state, is it clear that they should behave like dark matter or dark
So-
energy or something in the middle?
Yeah, because these are almost like a dark matter because these are heavy objects and compact objects. So this is almost like you have a dark monopole floating around. But in addition to the sort of the dark monopole profile, you also have a Higgs profile inside. So it's almost just like a simple modification which should not change sort of the overall, the omega.
And when you do your calculation for the baryogenesis side, okay, let me say it like this. How does the calculation change if instead of these balls, we had like other extended objects like strings or domain balls?
Good. Thanks for asking. So this was actually performed by Klein in '99. They actually thought of electroweak symmetric strings and actually doing this kind of calculation. I think you can do it. I think they faced a problem like not enough strings or something of that kind to actually do the baryogenesis. So the baryon asymmetry that they generate is a little bit smaller than what we generate. So that was the issue as far as I remember.
Is it because they're effectively lower dimensions?
Yeah, here you have a vacuum in a way where you can generate, but there you have some sort of like a string, like it's a 2-dimensional.
Gustavo.
My impression that you want the beta side to be very, very different than the beta. Not the Higgs atom, but the symmetry rating scale for the monopole. It's supposed to be very, very large compared to sort of the scale that would set the side.
Yes, that is where the 1 by G. So the size of the monopole is 1 by GF, right? Which is the, so here what we are saying is the G could be much smaller. And that is how you are getting sort of the larger size objects. Yeah. F could be larger, but G could be much smaller than that to get that. It's almost like you are getting much bigger monopoles by reducing the W gauge boson mass.
Let's thank Mrunal again.